Good morning, students. Welcome to Purnachandra Higher Secondary School. So in this session, we are discussing about another important topic of physics, that is your dielectric polarization and the effect of dielectric medium on the capacitance of a parallel capacitor. There are three important small sessions here. Dielectric, we have to first discuss about the dielectric medium or dielectrics. Next we are discuss about the polarization. Next we are discussing about the effect of the dielectric medium in the capacitance of the parallel capacitor. So first of all, let us discuss about the dielectric or dielectric medium. What are these things? Okay. So dielectric, these are, remember very one word, these are the insulating material. These are the insulating material in which the electrons are tightly packed. The electrons are tightly packed in the lattice structure around the nucleus. This is a very important one. Okay? So again I will repeat. Dielectric is a substance, is an insulating substance in which all the electrons are tightly packed in the lattice structure. In the lattice structure around the nucleus. So what does mean tightly packed? So tightly packed means there is no free electrons around it. Very simple. If there is no free electrons around it, then can it carry the current? No, it will not carry the current. That's why it is called insulating material. Okay, it's a very important. So dielectric, these are the insulating material. For example, like in the example of dielectric, just I have discussed, that is your mica, oil. These are the dielectric materials, mica, oils, etc. Quartz. These are, we can take it as a dielectric material, because in my previous session I have already discussed. Suppose this is a capacitor, okay, and the capacitance value of this capacitor depends upon the dielectric medium. I have already discussed. The medium can be air medium, and the medium can be other mediums. Other medium means dielectric mediums. I can also take it mica. I can also take it your paper, I can also take it electrolyte, and I can also take it oil, water, anything. So that means the dielectric substance or dielectric medium is nothing but the materials or the substances in which all the electrons around the nucleus are tightly packed, for which there is no free electron around it. Very simple. And these are the examples: mica, quartz, oil. These are the dielectric materials, and every dielectric material is a dielectric constant. Every dielectric material is a dielectric constant. The dielectric constant, I can denote it as a K, or it is also named it as epsilon r. I have already discussed epsilon r. Epsilon r is nothing but the relative permittivity, which is the definition or the notation, that is epsilon r, that is the permittivity of any medium divided by permittivity in the free space. This is the formula of dielectric constant, which I have already discussed in my physical class. Directly interaction classes, in these classes I have already discussed about the dielectric constant. I think students, you already remember that K is nothing but the dielectric constant, or it can be denoted as epsilon r. Epsilon r is called relative permittivity, is equal to permittivity divided by permittivity in the free space. This formula is very important, and it is a very important application in the last part. Whatever the last part mentioned in my heading, effect of dielectric medium on the capacitance, in this part this formula plays a very important role. Okay, so this is some of the important lines about the dielectric. Next, if one question arises, if the dielectrics are insulating and there is no electricity flowing in it due to the package, solid package of the electrons, or there is no movement of the free electron inside it, then what is the meaning of polarization? How this type of materials can be polarized? Let us discuss. Okay. So before moving into the polarization, we know that there are two types of molecules available. One is your polar molecules, another one is your non-polar molecules. Okay, there are two types of molecules. There is you are present in our universe. One is your polar molecule, another one is your non-polar molecules. In the non-polar molecules, remember, this is your figure 1. This pair is your, let us, I will name it as figure 1. The below one, I will name it as figure 2, this pair. Okay, so look at the figure 1. The figure 1 is the notation or the description about the non-polar molecules. Okay, so what are the non-polar molecules? Let us first discuss. Non-polar molecules is one in which the center of gravity, remember, non-polar molecules is one in which the center of gravity of the positive charge, that is the protons, and the negative charge become coincide. They will match each other, coincide each other. Look at the figure. Don't confuse. These are the electron clouds. These are the electron clouds, and these electron clouds is having a effective center of gravity. So that center of gravity and the proton center of gravity becomes match each other. They will say, that's why that type of molecules are called non-polar molecules. So in the general sense, these non-polar molecules will not have any dipole moment in general sense. But if we put the non-polar molecules in the electric field, look at here, suppose this is your direction of electric field. Okay, and I will place, look at this figure. Okay, I will place this same structure, the same non-polar molecule in the electric field. All of you look, the middle here, the positive center of gravity and the negative center of gravity both coincide, present at the center. But when it is present in the electric field, there is no field here, but there is an electric field here. Look at this. Okay, so in the presence of this electric field, look at the middle, the center of gravity is shifted somehow. You can easily verify from this figure. The center of gravity will shifted somehow. That means the electrons center of gravity, the proton center of gravity, they will not match if they are present in electric field. With the effect of electric field, they were somehow far apart. They will separate. Okay, separate means there is a distance in between the positive charge center of gravity and a negative charge center of gravity. Okay, so as we know from the discussion of electric dipole, what is electric dipole? Electric dipole consists of two charges separated by a small distance. So the same concept is here. Due to the application of electric field, the center of gravity of positive charge and center of gravity of the negative charges becomes little bit separate, very little bit separate. Okay, so due to the separation, there is a distance in between these two, and due to this, the non-polar molecule behave like a dipole, and that type of dipole is called induced dipole. Remember, it is that type of dipole which is arised in the non-polar molecule due to the presence of the electric field. That type of dipole is called induced dipole. That means in general sense there is no dipole moment is there or there is no dipole is there. But if we place the non-polar molecule in an electric field, then the electrons and protons are a little bit apart and they will behave like a dipole, and that type of dipole is called induced dipole. It's a very important concept in non-polar molecule. Okay, clear all of you? So induced dipole means that there is also a dipole moment. So the dipole moment is also called induced dipole moment. Very simple. Okay, so now let us take some of the examples of your non-polar molecules. I think all of you know nitrogen, hydrogen, oxygen. These are the examples of your non-polar molecules. Clear all of you students? Okay, so the figure 1, the pair, we discuss about the non-polar molecules. With the example is nitrogen, hydrogen, oxygen, etc. You can take other examples also. So there is the important term we will get, induced dipole. This induced dipole we will get due to the presence of what? The electric field. Okay, so let us discuss about the polar molecules. Now the discussion about the non-polar molecules finished. Okay, so let us discuss about the polar molecules. Clear? So when we will discuss about the polar molecules, what are the examples coming in your mind? A very familiar example is your water, H2O. Another familiar example is N2O. Another familiar example is NH3. So these are whatever the compounds we have mentioned here, H2O, N2O, NH3. Okay, so these are the examples of your polar molecules. Okay, so now as we have discussed just now, in the non-polar molecules what happens? The center of gravity of positive charges and the center of gravity of the negative charges coincide each other in general sense. But in case of polar molecule, this is not happening. As this is a polar, the name is polar. That means there is a permanent dipole developed there. Okay, so that's why it is developed, because in the polar molecules, very importantly in the polar molecules, the center of gravity of the electrons and the center of gravity of the protons, or center of gravity of the positive charges and center of gravity of the negative charges, they are not coincide, they are separated. So separated, look at this figure, you can easily verify. This is one of the very structural example of structural view where there is no field, there is no effect of electric field. So these are, look at here, these are the positive charges of protons and these are the negative charges. They are separated by a very small distance. Okay, so these are one dipole, they behave like a dipole. Polar, and these are the polar molecules, so that's why these have permanent dipole moments. Very simple. Okay, now let us discuss about the effect of electric field on it. Let us discuss about the effect of electric on it. Very simple. So now, as we have seen here, there is no field, there is no effect of electric field. Look at the dipoles. They are randomly moved, or they are randomly directed. Randomly directed means if I want to find out the effective or net dipole moment, can I find out? No, I cannot find out, because these are randomly moved. They have no certain direction. Very simple. Okay, so that's why there is no, I cannot find out the net. Okay, the net dipole moment or net dipole from this. But if this same structure, the same polar molecules are present in electric field, then what happens? All of you look at here. If I will put these non-polar molecules in the electric field, all the dipoles are perfectly aligned. Look at this figure. All the dipoles, these are not perfectly aligned, they are randomized. But in this case, all the dipoles are perfectly aligned along the direction of electric field. That is a very important one. All the dipoles, look at the figure, all the dipoles are perfectly aligned. Aligned means directed along the direction of the electric field. This process or this concept or this phenomenon is called polarization. Okay, so now I can simply define the polarization in this case, that the alignment of the dipole moments, remember the definition, the alignment, that means the direction, the alignment of the dipoles, okay, of the dipoles means of the permanent dipole or induced dipole. Very simple. Okay, so the alignment of the permanent dipoles or induced dipoles along the direction of electric field is called polarization or electric polarization. The name is electric polarization. Again I will repeat. The alignment or the direction or the alignment of these dipoles means permanent dipoles, or in case of induced dipoles along the direction of electric field is called electric polarization or polarization. Okay, so this is the very important concept in physics, that is electric polarization. So that means if the electric polarization, I will name it as P. If I name the electric polarization as P, then it is very much clear that the electric polarization is directly proportional to the electric field intensity. Both are vector quantity. Okay, so both are vector quantity, but if I take the magnitude, then the P value, that is the dipole moment value, okay, the electric polarization value is directly proportional to the electric field intensity. As the electric field intensity increases, the electric polarization also increased. Okay, so this is the important concept about the polarization, or in this way we can polarize a non-polar molecule and also we can polarize a polar molecule. In a non-polar molecule you will get induced dipole, but in case of polar molecules we will get permanent dipoles. In the induced dipole and also in the polar molecule, we have already seen that in both the cases we will get what type of polarization? The electric polarization. So these two concepts, I think all of you clear. Okay. So next we will move into our last part of our session. Okay, the last part of our session, the last part is your effect of dielectric medium on the capacitance of the parallel plate capacitor. Okay, that means I have to find out what is the effect of this dielectric medium. What is the effect of this dielectric medium if I will place the dielectric in between these two plates. Okay, so let us suppose these are the two plates. Again I will draw the figure. If these are the two plates, okay, one is your positively charged plate, another one is your negatively charged plate. Okay, this positively charged plate and also negatively charged plate is having a surface charge density sigma. Okay, so this is your plus q, this is your minus q, and in the previous parallel plate capacitor I will place what type of medium? The air medium. But in this case we are discussing about the dielectric medium. So let us place a dielectric medium in between these two plates. Okay, so this is your dielectric medium, a dielectric slab having a thickness T, Okay, so I will take the thickness of this plate as T. The distance between the two plates is the D. The area of the plate, becomes A. Okay, so these are the things. So again I will repeat, these are the two parallel plates. In between these two parallel plates I will put a dielectric slab having a thickness T. The distance between the two plates is a D. So this is the vacant region, this is my vacant region, both are same. So if this is a T and this is D, so obviously this is a D minus T and this is also D minus T. Okay, so in this part we have to find out what is the effect of this plate having a thickness T on the capacitance of the parallel plate capacitor. Clear? Okay. So in our same discussion, so this is the plate 1, this is the plate 2. So plate 1, you are generated some electric field. It's a very simple, because this is positive, means the electric lines of force generated from the positive plate move towards the negative plate. It's very simple. But here little bit different is that there is a your dielectric medium is there. So in between it, here also we are generating a negative one, and here we are induced a positive charge. Very simple, due to the induction of charge. Clear? Okay. So now due to this plate and due to this plate, already we have discussed in the parallel plate capacitor what is my net electric field intensity. The net electric field intensity, because for this plate is sigma by 2 epsilon 0, for this plate is sigma by, and already we have discussed in this one. So this is your 2 epsilon 0, this is your 2 sigma. So finally this is sigma by epsilon 0. Very simple, we have already discussed. This is due to this is a very important one. Due to this two plates, sigma by epsilon 0 in between these two. But here there is introduction of this dielectric medium. So let us find out what is the electric field, the value of electric field due to this. Okay, so here this is, let us take E dash. E dash what? E dash electric field due to dielectric slab. Okay, so in between the due to the dielectric slab, what is my electric field? Let us discuss. So electric field is equal to sigma divided by, this is your epsilon. Remember, this is epsilon 0 means this is your air space, but this is not air medium. This is any dielectric medium. So the dielectric medium is having a dielectric constant. Okay, so this is epsilon 0, epsilon r, very simple. So sigma divided by epsilon 0 and epsilon, there is introduction of your dielectric constant, only simple, there is nothing change in it. Okay, so again I will repeat, this is the value of electric field due to the air medium. This is the value of electric field due to the introduction of this dielectric plate in between having a thickness T. Okay, so E is equal to this much, E dash is equal to this much. Okay, now next part I have to find out the value of potential, electric potential due to this and due to this. Clear? Okay, so now, so let us find out the electric potential V. Okay, so first of all let us find out the electric potential V due to the electric field in this case, due to the electric field due to this dielectric medium. Okay, so now V is equal to E. Look at here, the space in between these, that means these and these, what is the distance? If this is T, this is D, then the gap becomes D minus T. Very simple. Okay, so E, that is V is equal to E into the distance. So what is the distance? D minus T. Okay, then plus E dash. E dash. So for E dash, what is my distance traveled? That is T, the distance traveled of the electric field, that is T. Okay, so V is equal to, for this gap, E into D minus T. For this part, E dash T, because these two become same, so any one of them I can take, either this or this equal to. So let us take any one of them. So E D minus T plus E dash T. Very simple. So let us put the value here. So that implies E value sigma divided by epsilon 0 D minus T plus sigma divided by epsilon 0 epsilon r T. Okay, so this is my electric field. Now from this we can take sigma divided by epsilon 0 common. Okay, if I take sigma divided by epsilon 0, what is the rest there? D minus T plus T divided by epsilon r. If from these two I can take sigma by epsilon 0 common. If I take sigma by epsilon 0 common, then what is the remaining inside the bracket? D minus T plus T divided by epsilon r. Okay, so this is the potential. This is the potential in between these two plates due to the effect of the dielectric. Okay, so here I will get. So let us put the formula into the capacitance. Let us put it. Okay, so what is the formula of capacitance? C is equal to Q divided by V. Very easy. C is equal to Q divided by V, and Q means there is a surface density sigma. So what is the value? Now sigma is equal to Q by A. So that implies Q is equal to sigma A. Very simple. So I will put this value here. Okay. So Q is equal to sigma A divided by, then put this value here. Okay. So V sigma divided by epsilon 0 D minus T plus T divided by epsilon. Okay, so let us solve this and you will get the answer. So let us solve this. So that implies C is equal to, so this sigma cancel out, this sigma and this sigma cancel out. Okay, so what is the remains there? Now epsilon 0 come to epsilon 0 A, okay, divided by D minus T plus T divided by epsilon. So this is this, let us name it as equation 1. Okay, so this equation, remember all of students, this equation 1 is the value of capacitance when a dielectric slab having thickness T is placed in between the two plates. This is the value. That is C is equal to epsilon 0 A divided by D minus T plus T by epsilon 0. Okay. Here we can take a special case. What is my special case? I think a question in your mind. Suppose this plate is fully covered in between these two plates. Suppose this plate, this whatever the plate I will take, the dielectric slab is fully covered the two or the full space. Then what happens? That means if the dielectric is fully covered the space. So if it is fully covered, then what is my T? T is nothing but D, because T and D both are same. So let us put it here in this case. So in this case, the capacitance E value epsilon 0 A divided by, so D minus T, so D is equal to T means this value remains 0 plus T. So here you can take also T, or here you can take, so D up to D. Let us take it as D. So D is equal to epsilon r. So what is the final value I will get? That is epsilon 0 epsilon r A by D. Remember, this is a very important formula. Finally, I will get this formula if it is. So there are two equations. One is equation 1, another one is equation 2. Look at the two ticks. One is equation 1, one is equation 2. Equation 1 and equation 2 both are important. Equation 1, when the dielectric slab thickness is T only, then this is my capacitance value. If the slab is fully covered in between the two space, then the thickness T is equal to the space distance, that is D. So if I put the value here, then I will get the capacitance is equal to epsilon 0 epsilon r A by D. Okay, so that means if there is no dielectric slab, suppose there is no dielectric slab, then in the previous video we have already find out the capacitance of a parallel plate capacitor. What is the value? Epsilon 0 A by D. We have already derived that one. For which medium? Air medium. Now I will place a dielectric medium. So there is nothing but a multiplication of epsilon r only. Epsilon r is nothing but a relative permittivity or dielectric constant. Okay. So now, if a question arises, listen the question very carefully. If a question arises, suppose a capacitance of a parallel plate capacitor in the air medium, then the value becomes E is equal to epsilon 0 A by D. Now, if I will introduce a dielectric slab in between these two medium, fully covered, then the capacitance value increases or decreases. Look at the equation. Into it, the epsilon r value becomes more. More means the capacitance value also increases. That is a very important question. Remember that question. If there is air medium, then the capacitance value of a parallel plate capacitor C is equal to epsilon 0 A by D. But if I introduced a dielectric slab in between these two plates, then the capacitance value becomes fully covered. That is very important. Fully, not half covered. Half covered means this is the formula. If it is fully covered, then the capacitance value becomes this, and the capacitance value becomes increases. At what times? How many times it will increase? Epsilon r times it will increase. And what is epsilon r? Epsilon r is a relative permittivity or dielectric